Okay, so in this video, I'm going to be working on question 3 from the second test from spring 2020. So here we're reading in the Titanic dataset. So here you'll note that I forgot actually to say family equals binomial, which means that this is not quite logistic regression. I chose not to fix it because, you know, whatever, those are still predictions. So I can still use them for the purposes of the question, no problem. Okay, so now here what I'm doing, and that's still in the question, that's still not the answer. So I'm getting the male and the female subset of the Titanic data frame, and now I'm computing the correct classification rate for male and the correct classification rate for female. As you see, not the same. So the first question is, well, like, is it not the same, but it's not the same, but is it statistically significant? Can we say for sure that this is not just due to random chance? Okay, so we need to compute the p-value. So the way I chose to compute the p-value is by a fake data simulation. So on average, the correct classification rate for men and women both is 79%. So my null hypothesis is going to be that the correct classification rate is really 79% if you had like lots of men and women. Now on the Titanic, it's a little bit questionable because actually kind of it's not as if you have lots of other people on the Titanic, but we kind of pretend. So, okay. So here I'm just computing and male and female just to use later. So more males than females there. So now I'm going to construct this fake difference function, right? So it's going to take the number of males, number of females, and the performance, the correct classification rate. Okay. And then I'm going to generate male CCR, female CCR. So the way I'm doing it is I'm doing our binom prob equals perf. So 1 corresponds to correct prediction and 0 corresponds to incorrect prediction. And perf, performance, is the probability of a correct prediction, right? Because if my probability of correctly guessing is 90%, then the CCR is going to be 90%. That's the same. And here what I'll do is I'll just compute the difference between the male CCR and the female CCR absolute value. Even though like here, the probability is exactly the same. So now I'll get 10,000 of those differences. So those are the ones. So, and I'm asking how often is this difference greater than 5.2%? 5.2% is the difference that I actually observe in the data set. And the answer is in this run, it turned out to be 7%. So I say, if this is how I set it up, I say I cannot reject the null hypothesis that actually the CCRs are the same. There's not enough evidence about that. So now let's do question 3b. So here the goal is to equalize the correct classification rate for female and for male passengers. So we actually discussed how to do that in the Fairness in Machine Learning lecture. And what we said is, well, I mean, there's no easy way to improve the performance for male passengers. If you could, like, you would have done that already. But what you can, so for female passengers, right? But what you can do is you can artificially decrease the performance for the male passengers, for which you currently are doing better in terms of predicting outcomes, right? So how would you do it? Well, for some of the males, you would just say, I'm going to flip my prediction intentionally. So I'm going to have a probability of getting the answer wrong. So what I'm going to do here is a sample calculation of how that would go. So it looks slightly complicated. It isn't really, but it's a little bit involved. So basically what I want is I want for the correct classification rate for males to be 76%, just like for females. And the way I'm going to do it is I'm going to say I want to flip the prediction for a fraction p of males, right? So because I'm getting most males right, I'm getting 81% correct. If I randomly flip some of the predictions, then my correct classification rate is going to go down. So the question is now, well, by how much am I supposed to be flipping the performance? And here's a little bit of a calculation. So basically, there's two situations here. So for 81% of the males, I'm predicting right. So if I'm flipping, then so if I'm flipping, then that means that in 81% of the cases, so in 81% of the cases, my correct classification rate, my kind of correct guess is going to turn into an incorrect guess. Okay, so in the others, it's going to stay correct. So this is 0.81 times the probability of not flipping. Those are going to be correct. So if in the 19%, if I flip, I actually flip from incorrect to correct, which means that in 19% of the cases, if I flip, I'm going to get correct. So the total number of correct guesses now is going to be, out of the 81%, 1 minus P are going to now be correct, because P means I'm flipping to incorrect. And out of the 19% that were incorrect, P are actually going to be correct. And P is going to be like pretty small, right? So basically I'm saying like, so imagine that we have 81 guesses and we have 19 guesses. So those are the incorrect ones, those are the correct ones. So what I'm saying is that there is a probability of 1 minus P that I'll get correct guesses out of this, because if I'm flipping, then it becomes incorrect. There's a probability P that's going to be pretty small, that out of those I'm getting something correct. And I want my correct classification rate, my new one, to be 0.76. Okay, so I just write this equation, and now I can just figure out what P is. So in this case, P is going to be 8%. So in 8% of the cases, I'm supposed to flip the prediction for males so that I get a 76% CCR for males. Okay. So you could have also done it experimentally, technically, kind of given the wording of the question. But anyway, so this is like that. And this is the accuracy for female, accuracy for male, 1 minus accuracy for male. Yes, 1 minus accuracy for male. And wait, what's 0.19? Yeah, 1 minus the accuracy for male. And this is the accuracy for male. Okay, so in fact, this is 1 minus 2 times male accuracy. Okay, so that's going to be like that. And I just translate it to the formula here to make a general P. So this function takes male accuracy, female accuracy. So now I'm making the prediction. And now I'm going to say, if the sex is male, then with probability P, I got to flip, right? So here I'm saying this. So our binom N1 size 1. So this is going to be 1 with probability P. So with probability P, I'm going to return pred smaller than 0.5. Otherwise, I'm doing the usual thing and predicting pred greater than 0.5. So that's the flipping. If the sex is female, then I'm not doing anything. I'm just returning the usual pred is greater than 0.5. So that's my pred pair accuracy. And now what I need to do is I need to just like make those predictions, make sure that things worked out for me. So I'll compute my male accuracy, female accuracy. We saw those numbers before. Hopefully they're the same. They're the same. So now what I'll do is a little bit of a trick, because I want to use this predict pair accuracy function on every row of the Titanic data frame, right? So in order to do that, I can't, because I have the if statements, I can't have vectors plugged in to predict pair accuracy. So what I'll do is I'll group by name. So if I group by name, then I have as many groups as I have rows, and each row is going to be in its own group because names do not repeat in the data set, right? So now I can just do that, and for each group of rows, which means for each row, I'll just mutate and say fair prediction is this. Okay, so this is kind of like a sneaky way of doing it. So in the solutions to precept 9, you've seen the same thing accomplished using row-wise, which is probably what you should be using instead of this trick, which is kind of like a tricky thing. But anyway, this works. So you could also have, of course, just did the vectorized computation, like any number of ways to do this. So here, what I'm doing is I'm getting, again, Titanic male, Titanic female. And here I have my performance for males. So it's 74.5. And this is 75.79 as before. So about right. So of course, it's going to be a little bit random. It's not going to be exact. But you see that those are much closer. So that is the infamous question 3.